This is our in-class work from December 4th and December 7th. If you missed class or just need to hear this again, hopefully this will be helpful. After listening to Trig property videos 1 and 2, you filled in the first page of your notes, and the first group of properties were the reciprocal properties, the quotient properties, and the Pythagorean properties. So I've got those listed here. Many times these properties are used to rewrite things in equivalent forms, but mostly they're going to be used to help get us to other properties that are going to be even more useful, particularly in calculus. So please hang on to all your trig notes and especially your trig property notes, because many students struggle with recalling that information at the beginning of calculus. So let's just look at a kind of problem called a trig identity. In a trig identity, we take the properties and apply them to show that one side of an equation is equal to the other. That's called an identity when there is no specific number in there. We have variables here, but we're saying for every value of x, this is always a true statement. I could do this on my calculator and show that this is true for a particular value of x. So if you might want to give that a try, put in some value for x, any value you want, as long as it's the same in all three, multiply those three together and verify to yourself that you actually get 1. But why is that always true? Well, it's true because cosecant of x is 1 over sine of x by the reciprocal property, and tangent of x is sine over cosine of x by the quotient property. So when we rewrite all of this in terms of the properties, we see we have cosine over 1 times 1 over sine times sine over cosine. The cosines divide out in the numerator and the denominator, and so do the sines, and we end up with just 1 equals 1, which shows that this side of the equation is always going to equal 1. QED is just a Latin phrase that stands for quod erat demonstratum. It's an abbreviation, which loosely translated means that which was to be demonstrated. It's usually placed at the end of a mathematical proof to indicate that the proof is complete, at least in the old school times. So let's just do one more of these. So we have sine squared of x, secant x, and cosecant of x. So I'm going to write this as sine of x times sine of x, and I'm going to write this over 1 because I'm going to end up making some fractions with the other ones. Secant x is the same as 1 over cosine of x. Cosecant of x is 1 over sine of x. And I want to prove that that equals tangent of x. Now I notice here that I have a sine in the numerator and a sine in the denominator. So sine divided by sine is 1, so I can simplify this fraction to just sine of x. Didn't really mean to change that to red for any particular reason. Sine of x over cosine of x. Well, we know from the quotient property that sine of x over cosine of x is tangent of x. Therefore, I have shown that the left side of the equation also equals tangent of x. Therefore, the left side equals the right side, and this is an identity. Some of these others are a little trickier, so I'm going to skip them for right now and do some other example problems on the other side. These problems are from Trig Property Worksheet number 1, which I attached to the live class event, which has your Zoom link in it, and you could open this file up and just look at it and write notes down, or you can also print it if you want to, but it's not required to print it. Okay, so let's look at our cofunction properties. Recall that in a cofunction property, we found that if two functions are cofunctions, the two functions are equal to each other if their arguments are complementary angles. In other words, if this is 21, this would have to be 90 minus 21. So 90 minus 21 gives me 69 degrees. So to make this statement true using the cofunction property, I would say cosine of 21 is sine of 69. Now in this one, you'll notice that the angles are complementary angles. This angle here is 90 minus 57. And you would have to notice that to know what to do next. Therefore, what does this function have to be? If this is secant, these have to be cofunctions of each other, so this one has to be cosecant. Now, to show you that this property still holds when the argument is negative, sine and cosine are cofunctions of each other, so sine of negative 15 should be cosine of 90 minus negative 15, which means this should be 105 degrees. So notice 105 and negative 15 are still complementary angles, even though one's greater than 90 and one is negative. We can also do this in radians. We say tangent of 2.5 is equal to the complement of 2.5 in radians, because cotangent and tangent are cofunctions. So what is comparable to 90 in radians? Well, recall that all the way around the circle, 360 degrees is 2 pi. Halfway around a circle is pi, which is 180. So a fourth of the way around a circle, 90 degrees, would be half of pi, which is pi over 2. So this should be pi over 2 minus 2.5, and if you evaluate, that would be cotangent of negative 0.93. Now that would be approximate, not exact. The exact value would be pi over 2 minus 2.5. So tangent of 2.5 and cotangent of negative 0.93, if you're in radians, are equivalent to each other. Now the next group of properties, if you look at these and take a look at your trig property notes for the first page, you'll notice that the ones that show like cosine equal to cosine, sine equal to sine, tangent equal to tangent are the odd and even properties. And basically in the odd and even properties, we know that cosine is an even function and sine and tangent are odd functions. We learned back in a previous unit that a function is even if opposite inputs give you the same output, and a function is odd if opposite inputs give you opposite outputs. So what we want to do is look and see, is this a true statement the way it's written here? Is this a true statement? So you might pause and just kind of look at them and see if you can decide which ones are true and which are false before I go on. Part A is a false statement. The reason it is a false statement is I don't have opposite inputs. What this one says is if I put the same number in, I get two different outputs, opposite outputs, which doesn't make sense. What we want to do is put opposite numbers in and get the same number out. So the way that this should be really written is that we would write cosine of 3.5 is equal to cosine of negative 3.5. And remember, when we look at a cosine graph, well, that's not a very good cosine graph. That's a really bad looking cosine graph, as a matter of fact. Let me try again. So here would be one cosine cycle, but we'd see on the other side of the x-axis, the y-axis, we'd see the identical values. So if I put 3.5 in for x and negative 3.5 in for x, we would get the same y value either way. Now here this says sine of negative 192 is equal to negative sine of positive 192. Here we see opposite inputs and we see opposite outputs. So we're saying if we put the opposite input in, we should get the opposite output. That is a true statement. When we go to C, we see opposite inputs, but we see that the outputs are the same instead of opposites of each other. This would say that tangent is an even function, but we know it's an odd function, so this is a false statement. What it should really say is tangent of negative 1.25 is equal to negative tangent of positive 1.25. That would be the true statement.